Hey there, everyone. Ready for another deep dive? Today we're tackling something pretty cool, an algorithm called DiscoTEX.
Sounds intriguing.
It's designed to solve a particular kind of math problem that you'll find in astrophysics,
Oh, what kind?
finding solutions to distributionally sourced partial differential equations.
This can be tricky.
Exactly. And we'll be using a research paper to break it all down. By the end of this, you'll have a good grasp of DiscoTEX, how it works, what it's good at.
Sounds good.
Let's get into it. The paper starts by talking about what makes DiscoTEX innovative. The way it combines these different techniques, like using discontinuous collocation for space and this implicit-turned-explicit Hermite formula for time. What makes those interesting choices from your perspective?
Well, discontinuous collocation, it really shines when you're dealing with discontinuities.
Oh, I see.
And those are inherent, right, with the delta functions and heaviside functions in these equations. So it's a natural fit.
Right, because those aren't your typical smooth functions.
Exactly. And then the Hermite formula, it's usually used for smooth problems, but here they've cleverly adapted it to handle discontinuities in time. Pretty neat.
So it's like they've taken these tools and sort of modified them to fit this specific challenge.
Yeah, exactly. Like specialized tools.
Cool. The paper then goes on to talk about these three key control factors: the number of nodes, n,
Right.
number of jumps, j, and the time step size, which they represent as shudder. I imagine these are all about kind of fine-tuning DiscoTEX, getting the best performance out of it.
Yeah, you got it. So the number of nodes, that's all about how finely you divide up your spatial domain. More nodes, higher accuracy, but you pay the price with computation time.
So it's a trade-off.
Always is. Then the number of jumps, well, that's pretty self-explanatory. It controls how many of those discontinuities you're allowing in your solution.
Makes sense.
And lastly, the time step size, that's your classic balancing act. Smaller steps, you get higher accuracy, but it takes longer to compute.
Gotcha. So finding that sweet spot is important. The paper then dives into a specific example, a distributionally sourced wave equation. Why did they pick that one, do you think?
Well, it's classic, both in math and physics. Plus, and this is key, it has a known exact solution.
So you can compare directly.
Exactly. You can see how well DiscoTEX does by comparing its solution to the actual answer.
That's a really good point. Having that benchmark is crucial. Now, walk me through how DiscoTEX actually solves this equation.
Sure. So they start off with the method of lines.
Okay.
Basically, that takes the PDE, the partial differential equation, and turns it into a system of ODEs, ordinary differential equation.
Right, breaking it down.
Exactly. Then comes the spatial discretization, using that discontinuous collocation method we talked about earlier.
Right.
This is where they handle those delta functions and heaviside functions, making sure they don't throw off the solution.
That seems like a crucial step. How do they manage those jumps?
It's quite clever. They use these piecewise polynomial functions to approximate the solution within each little section of the spatial grid.
I see.
And these polynomials, they're specially designed so they can actually have jumps right at the source.
So it's not just smoothing things over, it's incorporating the jumps themselves.
Precisely. That's how they get an accurate representation of solutions to these kind of equations.
Fascinating. Now, what about the time dimension? How does DiscoTEX handle that?
That's where that discontinuous time integration comes in, using Hermite interpolation. This method is great because it incorporates those jumps in the solution at specific points in time, making sure we're accurately representing how the source moves.
I'm curious about the Hermite interpolation. Why is that a good fit for this kind of problem?
Well, with Hermite interpolation, you're not just considering the solution's values at past time steps, you're also using the values of its derivatives.
Okay.
And this gives you a more accurate approximation, especially with those jumps, because it captures how fast the solution is changing around those points.
I see. So it's not just where, but how fast it's changing.
Exactly. This ensures DiscoTEX can track the solution even when the source is moving quickly, leading to more of those jumps.
They mention a 12th order discontinuous Hermite formula. What's the significance of that high order?
So the order of the Hermite formula, it refers to the degree of the polynomial used in the interpolation. Higher order generally means higher accuracy because it can better approximate how the solution behaves between time steps. Getting to a 12th order formula is pretty impressive. It shows the potential for some really precise time integration.
So it's like having a more powerful tool to zoom in on the solution as it changes over time.
That's a great way to put it.
But, as with anything, there's usually a trade-off. Does higher accuracy mean it takes longer to compute?
That's a great question, and it's something the paper addresses directly. They find that while higher orders do increase accuracy, the computational cost goes up significantly too.
Ah, there's that balance again.
Yep. The choice of which order to use depends on what you're trying to achieve and what kind of resources you have. They give the example of modeling these super asymmetric binaries, like XMRIs, where maybe higher orders aren't worth the extra computational burden.
Okay, let's dig into section 2, the DiscoTEX numerical recipe in a nutshell. They lay out the math problem they're tackling, a specific type of wave equation, and they use this special coordinate system called the hyperboloidal coordinate chart.
Right, and they describe it with this equation involving the D'Alembert operator acting on a field, which they denote as LM.
And, of course, it wouldn't be the same without those Dirac delta functions and Heaviside functions in there, making things interesting.
Exactly. It wouldn't be a true challenge without them.
It's great they have that known exact solution for this specific equation, though. That lets them directly compare DiscoTEX's solutions to the real deal and see how accurate it is.
Absolutely. It's a crucial step in verifying the method.
They also talk about finding a numerical weak form solution. What's that all about?
Basically, it means they're looking for a solution that satisfies the equation in a slightly less strict way.
I see.
And this is often necessary when you have those pesky delta functions and Heaviside functions involved.
Right, because it can create some tricky situations.
Exactly. Now, to represent the solution, they get pretty clever. They use this combination of two functions, a plus and a, and multiply them by Heaviside functions.
Interesting.
This setup allows the solution to have this jump across where the source is located, which makes sense physically. It's like modeling how a wave would behave when it encounters a sudden change in the medium.
Right, it's not just a smooth, continuous wave anymore.
Exactly. It needs that jump to represent the effect of the source.
Now, in section 2.1, they bring up the method of lines framework again.
Right.
I remember you mentioned that earlier. It essentially transforms that complex PDE into a set of ODEs, making it easier to solve numerically.
Right. It's like breaking down a complex task into smaller, more manageable steps.
So instead of having to deal with all the variables at once, we can focus on solving these ODEs, which only involve changes over time.
Exactly. And to make things even more compact, they introduce this new variable, u, which is essentially a vector that combines the field variable a and its time derivative a. This allows them to write the whole system of ODEs in this nice matrix form, which is perfect for numerical calculations.
Makes sense. They also emphasize that they're aiming for numerical weak form solutions to this system of ODEs.
Yeah, they reiterate that they're not necessarily after solutions that are perfectly smooth and differentiable everywhere.
Right, because those jumps can cause issues if we're too strict with our definition of a solution.
Exactly. Now let's jump into section 2.2, spatial discretization via discontinuous collocation methods. This is where we get down to the nitty-gritty of how they handle the spatial aspect of the wave equation.
Perfect. We've talked about the overall approach. Now let's see how they translate it into a numerical method.
So the core idea of spatial discretization is to represent that continuous space as a bunch of discrete points, like creating a grid.
Like pixels on a screen.
Sort of. Instead of trying to solve for the solution at every single point in space, which would be impossible, we focus on a finite number of points. That makes it a problem we can actually handle with computers.
Right, it's all about approximations that are good enough to give us meaningful results.
Exactly. And those points, those are called collocation nodes, and the choice of where they are is super important for accuracy. They suggest using something called Chebyshev pseudospectral collocation nodes. They have some nice properties for approximating solutions to these types of equations.
Cool, so they're being very specific about where to place those points to get the best results.
Yep, it's all about optimization. Now here comes the fun part. They introduce this piecewise polynomial function, which they call, to represent the approximate solution within each little interval of that grid. And this polynomial is specially designed to allow for jumps in the solution.
Ah, those jumps are back.
Right, it's got to incorporate the effect of those delta and Heaviside functions.
So it's not just a smooth curve, it can have those sudden changes.
Exactly. And the way they build this polynomial is based on these things called Lagrange basis polynomials.
Okay, tell me more about those.
They have this really neat property. Each one is equal to 1 at one specific node and O at all the other nodes. It's like a switch that's only turned on at that one location.
Interesting.
And this makes it really easy to stitch together the solution across the whole spatial domain while making sure that we respect the potential for those jumps right at the source.
So they're carefully controlling where the solution is allowed to jump based on where the source is located.
Precisely.
Yeah.
It's a really elegant way to handle those discontinuities. And to account for those jumps in the piecewise polynomial, they introduce this correction term. They call it EMRI. It involves the Heaviside function, so that jump only happens where it's supposed to. And there's a special function, creasejet, that comes in to control how big that jump is.
So it's like they're adjusting the height of the jump to match what the source is doing. What is that G function and how does it work?
Right, it's about fine-tuning. That G function, it's a polynomial, and its coefficients, they call them GM, are these user-specifiable parameters. So you have some flexibility to adjust how the algorithm handles different types of jumps.
I see. So you can tweak it depending on the problem.
Exactly. Now, the heart of the numerical method, how they deal with those spatial derivatives, they replace the continuous derivatives with these discrete approximations based on the values at the collocation nodes.
Right. Going from the smooth calculus world to the discrete world of computers.
Exactly. And that correction term, aura, comes into play here too. They adjust the derivative approximations to account for the jumps. That's crucial because those jumps could introduce big errors if you don't handle them carefully.
So it's all about making sure those jumps are captured accurately, both in how big they are and where they happen.
You got it. And one more neat detail in this section, they introduce this recurrence relation for calculating those GM coefficients.
Okay.
This allows you to calculate them efficiently for different orders of jumps, which is great for optimizing performance.
So it's not just accurate, but also efficient.
Yeah.
Nice.
Now let's move on to section 2.3, discontinuous time integration via Hermite interpolation at higher orders. Remember those ODEs we got from the method of lines? Now we got to figure out how to solve them in time.
Right, the spatial part is taken care of. Now it's time to deal with how things evolve over time.
The classic approach is to break up time into these little steps and then approximate the solution at each step based on what happened at the previous steps.
Like taking snapshots at regular intervals.
Exactly. But as you might have guessed, there's a catch. We got to account for those discontinuities in time caused by the source moving around.
Those jumps are back to haunt us.
They always find a way. To handle this, they use a clever technique called Hermite interpolation. It goes beyond just using the values of the solution at previous times. It also uses the values of its derivatives. And that allows for a much more accurate approximation, especially when you have these jumps, because it captures how fast the solution is changing around those points.
I see. So again, it's not just about where the solution is, but how quickly it's changing.
That's the key. They introduce this piecewise polynomial function, similar to what we saw for the spatial part, but now it's a function of time. And this polynomial is carefully constructed to have a jump at a specific time, tex, which is when the source crosses a grid point in space.
So they're essentially predicting when those jumps are going to happen and incorporating that into how they integrate over time.
Precisely. And to figure out the coefficients of this polynomial, they impose a bunch of conditions. Some conditions make sure the polynomial matches the solution and its derivatives at the beginning and end of the time step.
Makes sense.
Other conditions enforce the correct jump in the solution and its derivatives at that special time, tex.
So they're really fine-tuning this polynomial to fit the solution perfectly, both when it's smooth and when it jumps.
Exactly. And by solving for these coefficients, they get this really powerful formula for approximating the integral of the right-hand side of our ODEs, which is exactly what we need to move the solution forward in time. They call this the discontinuous Hermite interpolation scheme.
Wow. It sounds like a really intricate way to deal with those jumps in time. How do they know the scheme actually works?
Well, they put it to the test. They have this whole example where they use a specific function, a time-dependent Legendre polynomial, that they know has a discontinuity.
Okay.
They calculate the analytical jumps in this function and its derivatives, and then they use their discontinuous Hermite scheme to numerically approximate its integral.
So it's like a controlled experiment. They know the answer beforehand and they can compare.
Exactly. And the results are fantastic. The numerical error scales really nicely with the order of the scheme, meaning higher order schemes give you much smaller errors.
That's great. So it
Yeah.
really does a good job of capturing those time jumps.
Oh yeah, it really shines in that regard. And to really drive home the point, They compare their discontinuous Hermite scheme to a regular, smooth Hermite scheme that doesn't account for the jumps. And guess what? The smooth scheme gives terrible results. It just can't handle those discontinuities properly.
That's a pretty convincing demonstration of why you need this special approach.
Right. It's not just a matter of taste. The smooth scheme just fails miserably in this case.
Now, they also looked at how the computation time changes for different order schemes, right?
They did. And unsurprisingly, higher order schemes take longer to run. It highlights that trade-off between accuracy and computational cost again.
So there's always that balance to consider.
Always. And this sets the stage nicely for the next part, where we'll see how they combine all these techniques into the full DiscoTEX algorithm.
All right, we've seen the building blocks, the spatial and temporal parts. Now let's see how they all fit together to solve the whole wave equation.
Picking up where we left off, let's dive into Section 3, numerical weak-form solutions to distributionally sourced partial differential equations via DiscoTEX generalization to higher orders. This is where the magic happens, where they assemble all the pieces into the complete DiscoTEX algorithm.
This is what we've been building towards, seeing how they take those spatial and temporal discretization techniques and make them work together to tackle the full problem.
Right, and they start by recapping the distributionally sourced wave equation, introducing some shorthand notation for the D'Alembert operator, using various coefficients like s and so on, which depend on that spatial coordinate.
And let's not forget that source term. That's the one causing all the jumps. They're going to tell us exactly how to deal with that numerically.
Absolutely, they'll break down all the details. They then remind us about the method of lines, where they introduce that vector variable u, containing both the field and its time derivative . This leads to that compact matrix equation for the time evolution of u, involving a spatial differential operator L, and of course that pesky source term s.
And they bring in this new term, or, which seems crucial for handling those discontinuities in time.
Right. That term acts like a switch, turning on corrections to the solution whenever the source crosses a grid point in space.
Smart. It's like anticipating those jumps and having a plan in place.
Exactly. Now, because we're in that special hyperboloidal coordinate system, they also provide the explicit transformation from the usual TX coordinates to the SAW coordinates.
Right. It's setting the stage for those calculations.
And then they dive into how those spatial derivatives in the operator L are handled using the discontinuous collocation method we talked about earlier, showing how those correction terms, and naka, are incorporated to maintain accuracy across the jumps.
Making sure nothing gets lost in those sudden transitions.
That source term s gets some special attention too. They show how to calculate its spatial derivatives, which are needed for those higher-order time integration schemes.
Right, making sure everything's consistent. And this is where those jam coefficients we talked about earlier, the ones that control the magnitude of the jumps, really come into play, right?
Exactly. They provide these clear formulas for calculating the source term corrections, considering both the spatial derivatives and those jump coefficients.
So they're really meticulously accounting for every aspect of those jumps.
Absolutely. No detail is overlooked. Now, remember those higher-order time derivatives of the source term needed for the Hermite interpolation?
Yeah.
Well, those weren't explicitly given in the original wave equation, so we got to derive them.
It's like a puzzle, figuring out the missing pieces.
Exactly. And they walk us through it step by step, showing how to use the structure of the equation to get those derivatives. Then they present the sixth-order Hermite time integration rule, the heart of the DiscoTEX algorithm.
Okay, this is where it all comes together.
This rule, it involves the values of the solution and the source term at the current and previous time steps, but also their first and second time derivatives.
Higher order, more information, better accuracy.
That's the idea. And to use this sixth-order rule, we need those second-time derivatives of the source term we just derived. They explain how to incorporate those into those discretized spatial differential operators.
Okay, it's all starting to click into place.
They even introduce the shorthand notation to represent the source term and its spatial derivatives in a compact vector form. It makes those equations a bit easier to read.
Always appreciate a little simplification.
Right. Now, they introduce those higher-order corrections to the spatial discretization, effiration. These involve the time derivatives of those jam coefficients, adding another layer of complexity.
Things are getting pretty intricate.
They are, but they don't leave us hanging. They give us a clear explanation of how to calculate those time derivatives using the chain rule and the known time dependence of the source's location.
It's like assembling a complex machine, making sure every gear and cog fits perfectly.
That's a great analogy. And then they give us the explicit formulas for the corrected spatial differential operators, taking into account those higher order corrections and the jump coefficients.
Like a recipe for a delicious numerical solution.
Exactly. And they emphasize that you got to apply those spatial derivatives in the right order, always acting on the field variable from the left. And they give us this handy tip. When you have coefficients that don't involve spatial derivatives, just multiply them by the identity matrix. It helps keep those matrix operations consistent.
Ah, those little details can make all the difference in getting things to work properly.
Absolutely. It's all about the details. And finally, they present the main event, the full DiscoTEX H6 algorithm, written in this concise matrix form.
The culmination of all that hard work.
It is. This algorithm combines all the pieces we've discussed: spatial discretization, Hermite interpolation, source term corrections, jump handling into this powerful engine for solving distributionally sourced wave equations.
Wow, it's quite impressive when you see it all laid out like that.
Right. It's like watching a well-oiled machine in action. The algorithm involves a series of matrix multiplications and additions, carefully orchestrated to step the solution forward in time while handling those jumps accurately. And it includes those JH6 Keras terms, which represent the contributions from the jumps in the Hermite interpolation scheme.
And those JH6 terms, they involve 6 jump coefficients, J0 to J5. I remember seeing those in the appendix. They have these long expressions for them.
Right. They carefully worked out those expressions, taking into account the specific form of the wave equation and the coordinate transformation.
Lots of details to keep track of.
Definitely. They even point out that higher order versions of DiscoTEX, like H8, H10, and H12, would require even more jump coefficients, making the algorithm even more complex. But for now, we're focusing on this elegant 6th order version, H6.
Which sounds like a good balance between accuracy and complexity. Now let's move on to section 3.2, where they switch gears and talk about how well DiscoTEX actually performs. Time to see if it lives up to the hype.
Exactly. They've laid out the theory. Now it's time to see how it performs in practice. They start by emphasizing that their goal is to showcase the capabilities of the algorithm and compare its performance at different orders.
Makes sense. They want to see how different versions of DiscoTEX stack up against each other.
Right. They use the same setup as in their previous work, with a specific temporal and spatial domain, and they remind us that they're working in that special scry-fixing gauge to ensure numerical stability at infinity.
Right, setting the stage for a fair comparison.
And to measure how accurate DiscoTEX is, they use the relative error, denoted by E. That's simply the difference between the numerical solution and the exact solution, divided by the exact solution. Smaller error means better performance.
So it's a straightforward way to quantify how close they are to the truth.
Exactly. Now, those 3 control factors we talked about earlier, N, J, and app, they play a big role in optimizing the algorithm's performance.
Right, those knobs you can tweak to fine-tune things.
Exactly. They remind us that for an optimal implementation, you got to carefully study how the accuracy depends on each of these factors.
Finding that sweet spot for each scenario.
Right. They start by verifying the convergence order of DiscoTEX.
Okay, what's that?
It tells us how quickly the error decreases as we make the time step size smaller, and they find that DiscoTEX H2, H4, and H6 all converge to their expected orders. So as we shrink the time step, the error decreases as it should. It's a good sign that the algorithm is working as intended.
So the math checks out.
Exactly. Then they look at those other 2 control factors, N and J. They fix a particular time step size and vary the number of nodes and the number of jumps, seeing how the relative error changes. They discover that using N 45 and J equals 19 gives them an optimal implementation for DiscoTEX H6.
So they're really digging into the details to find the best settings.
Oh yeah, they're being very thorough. And to compare the performance of different order algorithms fairly, they use the same time step size for all their simulations. That way, any differences in accuracy are due to the order of the algorithm itself, not just because one is using smaller time steps.
Makes sense. It's like running a race where everyone starts at the same time so you can see who's truly faster.
Right. Now, the results are really interesting. They find that while higher order algorithms do improve accuracy, the difference isn't as dramatic as you might expect. For instance, the difference between the 4th order and 6th order algorithms is pretty small, especially at a given time step.
So it's not always a straightforward higher order is better situation.
Nope, there are nuances to consider. To explore that trade-off between accuracy and computational cost further, they analyze the computation times for all 12 orders of DiscoTEX.
Okay, and what do they find?
Well, The results are pretty striking. The computation time increases significantly as you go to higher orders, but the accuracy doesn't really improve much beyond the sixth-order algorithm. This suggests that for a lot of applications, that sixth-order version might be the sweet spot, providing a good balance between accuracy and speed.
So it's not always worth going all the way up to the highest order.
Exactly. And they offer some insights into why this happens. The key factor seems to be the presence of those time-dependent jumps.
Those jumps are causing trouble again.
It's like they're the bottleneck. Handling them numerically requires extra computations, and those computations get more demanding as you increase the order of the algorithm.
So the more complex the algorithm, the harder it is to handle those sudden changes.
That's a good way to think about it. Now, they circle back to the question of whether you always need to use the highest order algorithm. They point out that for certain applications, like modeling those highly eccentric EMRIs, where the source is moving very rapidly, using a higher order algorithm might not be worth the extra computation.
Right, because the source is zipping around so much that those jumps become more frequent and harder to manage, right?
Exactly. But there's a silver lining. They point out that higher order implementations of DiscoTEX can reach higher accuracy faster for longer time steps.
Okay, so there are situations where it might be beneficial.
Right, like if you need extreme precision, but the source is moving relatively slowly, then those higher order algorithms might be a good choice.
So it depends on the specific problem you're tackling. It's not a one-size-fits-all situation.
Exactly. They even suggest another application where higher order DiscoTEX could shine, modeling those extremely asymmetric binaries like XMRIs, where the source might be on a nearly circular orbit.
So in those cases, the jumps would be more predictable and easier to handle.
Exactly. It all comes down to the specific details of the problem. Now we're at section 4, the conclusion. The authors do a nice job summarizing their findings, highlighting that key trade-off between accuracy and computational cost as you go up in the order of the algorithm.
Right, it's not a free lunch.
Yeah.
You always have to balance those factors when choosing a numerical method.
Exactly. Then they jump into potential applications for higher order DiscoTEX. They acknowledge that for cases with those time-dependent point particle trajectories, like those highly eccentric EMRIs we talked about,
Yeah.
those higher order versions could be really computationally expensive, especially if you want to compute the self-force on the particle.
Makes sense. When that source is moving so rapidly, all those jumps become a real headache to handle numerically.
Right. But they do offer a glimmer of hope, pointing out that higher order implementations of DiscoTEX can get to that high accuracy faster for longer time steps.
Oh, interesting.
So it's not a complete no-go. There might be situations where it makes sense, like if you need that super high accuracy, but the source is moving relatively slowly.
So it really depends on the specifics of the problem.
Always does. They even highlight a specific scenario where higher order DiscoTEX could be really useful. Modeling those extremely asymmetric binaries, like XMRIs, where the source might be on this nearly circular orbit as it spirals in.
So in those cases, the jumps would be more predictable and easier to handle for those higher order methods.
Exactly. They also suggest another interesting application for that IMTEX Hermite time stepper, both the discontinuous and smooth versions, black hole spectroscopy.
Okay, what's that about?
Well, it involves studying these characteristic oscillations of black holes, called quasi-normal modes.
I've heard of those.
And these modes can tell us a lot about the properties of the black hole.
So DiscoTEX could potentially help us learn more about these fascinating objects.
That's the idea. And that wraps up the paper. They leave us with a sense of excitement about the potential of DiscoTEX and similar algorithms.
I like how they end with a call for further exploration. They focused on the accuracy and speed of DiscoTEX.
Right.
But there are so many other aspects of this algorithm that are worth investigating.
Absolutely. They even suggest looking into the stability of DiscoTEX, which is always crucial for numerical methods.
Right. You want to make sure your algorithm isn't going to go haywire.
Exactly.
Yeah.
And they also mention exploring how DiscoTEX connects to other numerical methods that could lead to some really interesting new techniques.
It's great to see a paper that sparks so many new questions and avenues for research. This deep dive has been a real eye-opener for me. What are your biggest takeaways?
For me, it's that balance between accuracy and computational cost. That's always a key consideration in numerical analysis, and it's really highlighted in this paper. Also, the ingenuity of their approach, the way they've carefully crafted these methods to handle those jumps and discontinuities, it's really impressive.
Agreed. It shows that even with these really complex problems, with those tricky delta functions and all that, we can develop sophisticated tools to get accurate and meaningful results.
Exactly. It's a testament to the power of numerical methods and their ability to help us understand these fascinating phenomena in physics and astrophysics.
And for our listeners out there, what are some things they can ponder as they continue their own explorations?
Well, think about those other mathematical properties of DiscoTEX that the authors mention. Could we analyze its stability in more detail? How does it connect to other numerical methods? And what other applications could it be useful for? There's so much more to discover.
This paper is really just the beginning of a much larger journey. And that's what's so exciting about research. There's always more to learn and explore.
Absolutely. So keep asking questions, keep digging deeper, and who knows what amazing discoveries you might make.
Well said. Thanks for joining me on this deep dive. It's been a pleasure exploring the world of DiscoTEX with you.
My pleasure. Always happy to talk math and physics.
Until next time, keep exploring the fascinating world of mathematics and all its possibilities. Hey everyone, welcome back. Today, we're going deep on DiscoTEX.
Oh, nice.
But not just like the intro stuff.
Yeah.
We're going to look at higher order implementations.
Okay.
What that means when you're trying to solve some really tough problems.
Yeah, the accuracy thing is always interesting.
Yeah.
We talk about it a lot, but we rarely see like what the trade-offs really are.
Yeah.
And this paper, they go all in.
Yeah.
Like, how far can we push DiscoTEX to these higher orders, you know?
Yeah.
Order 12 even.
I gotta admit, when I saw Order 12 in the title, I was like, whoa, hold on.
Yeah, it gets pretty wild.
So it's not just like, here's DiscoTEX.
Right,
It's
right.
how far can we take this thing?
Exactly.
And they use a wave equation as their example.
Smart choice, actually.
Huh. Why is that?
Because this particular wave equation, it has exact solutions.
Okay.
So you can compare what DiscoTEX does,
Ah, I see.
especially at those higher orders.
To the ground truth.
Exactly. Like a perfect control in an experiment.
Makes sense.
Yeah.
Okay, so section 2, they jump right in.
Yeah, discontinuous time integration. They're not messing around.
It's pretty dense already.
Well, the core idea is they're using these piecewise polynomials.
Okay.
It's basically, instead of assuming a smooth curve for the solution,
Right.
they're breaking it up
Yeah.
into smaller pieces, little segments,
And that lets them handle what?
to jumps, the discontinuity.
So it's more like a staircase.
Kind of, yeah.
Hmm.
But much more sophisticated, obviously.
I'm looking at equations 46 and 47 for the 12th order.
Oh, yeah, those are something else.
Nearly gave me a headache. What's the takeaway for someone who's, not going to code this up themselves?
Think of it like this. Those equations, they're the heart of how they deal with the jumps at that crazy high order.
Okay.
They're complex because they're capturing a ton of detail, very nuanced behavior.
But there's that term, JH12,
Right. That's where the jump is, mathematically speaking.
like a little mathematical shock absorber.
Uh-huh. Kind of. Smoothing out the bumps in the solution.
Okay. But we got to see how this performs, not just the equations. right?
Absolutely. Figure 1 and Table 1, that's where the rubber meets the road.
So figure 1 is showing what the error.
Yeah. Visually, each line is a different order, and you see they're all sloping downwards.
So that means
Error is shrinking. Higher the order, steeper the slope, less error.
okay, that's intuitive. But table 1.
That's where the trade-off starts to show up.
What do you mean?
They list the computation time.
Right.
And it's clear, you go to those high orders, time explodes.
We're talking like minutes versus hours.
Oh, yeah, easily. Which, makes you think, how useful is this, really?
Right, because if it takes a week to run, who cares how accurate it is?
Exactly. Suddenly, that good balance they mention, it makes a lot more sense.
All right, section 3 is where they actually apply this to the wave equation, right?
Right. This is where the theory meets the real problem.
What are the main steps here?
So they walk us through correcting those evolution operators.
L1 and L2, right?
Yep. To handle discontinuities, but not just in time, in space, too.
Oh, wow. So it's getting more dimensions involved.
It does. And then there are these OR terms they introduce.
Yeah, in equation 64 and 68, what are those about? They look kind of Greek to me, pun intended.
Haha, yeah. Think of them as triggers.
Triggers.
Yeah, they activate when that point causing the discontinuity, it crosses a grid point.
Remember, we're breaking the problem down into lines.
Right. These terms, they make sure the solution jumps correctly between those lines.
Okay. So it's like, hey, Something's changing here.
Exactly, a little signpost along the way.
But then it gets even more complex.
Oh, yeah, equations 86 through 92, that's where they get into the spatial corrections.
What's happening there in simple terms?
So they're using this vector g and its higher order derivatives to handle the spatial jumps.
Okay.
But the key is they avoid needing diagonalization.
So less computational overhead.
Exactly, which is huge GE because those high orders are already taking forever.
All right, got to save time wherever we can. Okay, equation 93. This is the DiscoTEX H-fix algorithm itself.
The combination of all those corrections all in one equation.
What are the main parts here?
Well, you see, JH6 is back.
So they've combined the time jumps with the spatial solution now.
Exactly, it's all coming together.
And figures 2 and 3, they're giving us a visual, right?
Yep, figure 2 is the wave solution, figure 3 is the phase portrait.
Are those matching what we'd expect to see?
Yeah, it's consistent with the behavior from the lower order stuff.
So that gives us confidence that even though it's more complex?
It's still working as intended. The core idea is sound.
Okay, good. Figure 4 is interesting. They're trying to find the optimal number of nodes and jumps.
Yeah, optimizing the setup.
What did they learn there?
That 45 nodes and 19 jumps gives a good balance.
Okay.
But what's interesting, going from second to fourth order, big difference.
Makes sense.
But fourth to sixth, not as much.
Diminishing returns again.
Exactly.
Like maybe there's a limit to how much accuracy is worth it.
Right. In stage 5, this confirms something we were hoping for.
What's that?
That the solution is converging at the expected rate for different orders.
So the theory and the actual implementation, they're lining up.
Perfectly. It's like those science experiments in school where it actually works.
Love those moments. Okay, table 2. This is the big reveal.
Yes, how much does that accuracy cost you?
Play it on me.
Higher orders, they do get you better accuracy, no doubt.
Right.
But the cost, computationally, it's sky high.
Okay, so maybe there's a sweet spot.
They really highlight DiscoTEX H4. That might be the Goldilocks zone.
H4, not too hot, not too cold.
Haha, exactly.
Before we wrap up part 1, what really stood out to you in all this?
Honestly, the way they handle the spatial discontinuities without diagonalization is just so clever.
Yeah.
It shows they're thinking about efficiency even while pushing for those higher orders. It's not brute force, it's elegance.
Great point. All right, folks, that's a wrap for part 1 of our deep dive into higher order DiscoTEX.
Buckle up.
We've seen the math, the challenges, and maybe a hint that higher isn't always better.
Part 2, we'll see what this all means for the real world.
Stay tuned.
Absolutely. Welcome back. Ready for more DiscoTEX?
Definitely. Still thinking about that whole diminishing returns thing?
Yeah.
More accuracy, but at what cost?
Right.
So, conclusions. What's the big takeaway? After all that math.
It really comes down to that tension, accuracy versus how much computing power you need. Higher orders are tempting, but they come with a price.
Yeah, especially they mention time-dependent trajectories.
Oh, absolutely. If the thing you're modeling is moving around,
right.
Those extra calculations, they really start to add up.
So it's not just the algorithm itself.
No.
It's the nature of the problem you're throwing at it.
Exactly. But they do point out some cases where it might be worth it.
No?
Even with that cost, they mention like extremely massive black hole binaries.
Okay, those are some seriously intense systems. Why is DiscoTEX good for that?
Because the scales involved, they're just mind-boggling.
Yeah.
And you need that crazy high accuracy to capture the little details.
So for those edge cases where you need to be super precise,
even if it takes longer,
you got to go higher order.
Might be the only way. They also mention black hole spectroscopy.
Which is?
Analyzing the light coming from matter falling into a black hole.
Okay.
Again, accuracy is like the most important thing there.
It's wild. This one algorithm.
I know, right?
From theoretical waves to actual black holes.
Uh-huh.
But they do say there's more to explore.
Oh, yeah. Always more to do.
What are some of the open questions?
One thing they highlight, comparing DiscoTEX to other algorithms.
So like benchmarking it.
Yeah. See how it stacks up, accuracy and efficiency.
See where it wins, where it needs work.
Right. They specifically mention conservative self-force computations.
Ooh, now we're getting fancy.
Yeah, this is key for modeling EMRIs.
EMRI, that's
extreme mass ratio and spiral. Small object, big black hole.
Those cosmic dances we talked about.
Exactly. DiscoTEX to like choreograph the black hole movements.
That's a great visual. And they're interested in eccentric orbits, right?
Yeah, where the path is not a nice circle, much harder computationally.
So even within those specific applications.
Neural levels.
Yeah. pushing the limits of what we can do right now.
But they've laid a good foundation, the authors.
Mm-hmm.
Robust algorithm, versatile, could change how we understand all sorts of things.
It does feel like we're just scratching the surface here.
Oh, for sure.
From your perspective,
Yeah.
what are the big hurdles to actually applying this to those crazy problems?
Computational cost is still king, especially for the time-dependent stuff. Higher orders, even with clever tricks.
You hit a wall.
It's a balancing act. Accuracy versus what's actually doable.
So sometimes it just comes down to raw power, how fast your computers
And a
are.
lot of times, yeah. But also adapting the algorithm to each problem.
Okay.
DiscoTEX is great, but each situation has its quirks.
Not one size fits all.
Exactly. Gotta tailor it to the specific cosmic dance, so to speak.
I like that. So you need both sides, the mathematicians and the astrophysicists.
Working together. In this paper, it's a great example of that.
Mm-hmm.
They built the tool A&D, showed how it can be used all over the place.
It is pretty amazing how this abstract math
I know.
actually tells us about the universe.
So cool.
All right, folks, that wraps up part 2 of our higher order DiscoTEX deep dive.
Well, one more to go.
We've seen the conclusions, potential uses, and the challenges ahead.
Join us for part 3. We're going even deeper.
All right, final part of our DiscoTEX adventure. We've seen the big picture, but I love that this paper, they really get into the details.
They do.
So appendices, where the math really gets intense.
This is where it gets fun.
Okay, for some of us. Appendices, they're often overlooked.
Right, but here, they're crucial.
Yes.
This is how the sausage is made, so to speak.
If the sausage is higher order, DiscoTEX. Okay, Appendix 8.1.
They jump right in, those time integration schemes.
Like a recipe book for all those crazy formulas we've been talking about.
It's more than that. It's like the annotated version. Oh,
They show you the steps, how they got there.
so it's not just, here's the equation.
No, it's a derivation, a masterclass.
All right, I'm grabbing my mathematical notepad. Equations A.1 through A.10 are those the different order integrators.
Spot on. Each one is a different order, from the simplest all the way up.
So you see how it builds as you want more accuracy.
Exactly. Like level 1 chef to master chef, the complexity increases.
Appendix A.2 seems to be about spatial discretization.
Right. Those jumps across space.
Yep. They're giving us the whole framework here.
Making sure the solution starts correctly, super important.
Setting the stage before the show begins. Yeah. I like that analogy.
I'm seeing some interesting symbols in equations A11 and A12.
Oh, yeah, like back and ux. Those are specific to the problem.
Okay.
Space-time geometry, the particle's path, all that gets factored in.
So it's like making sure the actors are in their places before the curtain rises.
Everything has to be just right.
Appendix 8.3, this looks like the heart of the higher order algorithms themselves.
This is it, the full machinery revealed. H2 all the way to H12, laid out.
Like seeing the blueprints for these different DiscoTEX machines.
Each one more intricate than the last.
And then equations A.13 to A.25, they're introducing even more stuff.
Higher order derivatives, more corrections, all to get that accuracy.
It's like adding those fine details to a painting makes it pop.
You got it. But remember, more detail, more computational cost.
Always that trade-off. Finally, A.4, the grand finale.
Time jumps. Making sure the solution stays accurate as the discontinuity moves.
Like the choreographer's notes for a really complex dance.
Each step has to be timed perfectly.
Equations 8.26 through 8.67, that's a lot of equations.
It is dense, but remember, this is for those who really want to dig in.
Yeah, the hardcore math folks.
The ones who want to build their own DiscoTEX from scratch.
It's amazing how much work went into this algorithm.
It really is. Meticulous research, the elegance of math, it's all there.
And they didn't just give us the final answer.
Right.
They showed us how they got there.
The challenges, the insights, the whole process.
It's like they're saying, come join us on this journey.
Yeah, exactly. Science isn't just about the result, it's the journey.
Well said. I think this has been a really eye-opening deep dive into DiscoTEX.
I agree.
From the basics all the way to this deep math.
It's been quite a ride.
And the most exciting part, this is just the beginning for DiscoTEX.
Oh, for sure. It's going to change how we do things.
All sorts of fields, astrophysics, engineering, who knows what else.
It's pretty inspiring to think about what's possible now.
So to everyone listening, keep exploring, keep asking questions, keep pushing the limits.
You might be the one to make the next big DiscoTEX discovery.
That's a great thought to end on. Thanks for joining us on this deep dive. It's been a pleasure.
Likewise. Until next time.
Take care, everyone. Welcome back, everyone, for another deep dive. This time, we're really getting into the weeds, a paper about numerical methods for solving PDEs.
Oh, fun.
Right. So it's all about this method called DiscoTEX
Okay.
for computing numerical weak-form solutions to distributionally sourced PDEs. And get this.
Okay.
This paper is trying to extend DiscoTEX to achieve, like, even higher orders of accuracy. We're talking 12th order.
Wow.
Yeah. I'm excited to see how they pull that off. Luckily, I've got an expert here to help us unpack all the math. What's fascinating about this paper is that it's not just like presenting a brand new algorithm. It's building on previous work
I see.
and refining it to achieve these pretty impressive results. What do you think?
Yeah, absolutely. The paper definitely states that DiscoTEX is an extension of the methods introduced in a previous paper from 2021, with the goal of reaching even higher orders of accuracy and longer simulation times. This is really important, I think, for challenging problems, particularly in astrophysics, like modeling extreme mass ratio and spirals.
Oh, yeah.
Getting accurate long-term predictions for those systems requires minimizing numerical errors, and that's where those higher order methods really shine.
Right. To achieve this 12th order accuracy, this paper uses some pretty intricate mathematical techniques.
Right.
One of the first things that jumped out at me was the method of lines framework.
Okay.
They break down the problem into spatial and temporal discretizations. Can you walk us through how that works?
Sure. The method of lines is a really common strategy for dealing with time-dependent PDEs. You essentially separate the spatial and temporal parts of the problem. First, you discretize the spatial domain, which means you're representing the solution at a finite number of points. This transforms the PDE into a system of ODEs that depend only on time. Then you can apply a suitable time integration method to solve those ODEs, effectively marching the solution forward in time.
Makes sense. Now, for the spatial discretization, they use discontinuous collocation methods. I'm curious about their choice of basis functions. They specifically mention using Chebyshev pseudospectral collocation nodes.
Right.
Why Chebyshev, and what makes them so well suited for this problem?
Okay, so Chebyshev nodes have some really nice properties for numerical approximation.
Okay.
They're based on the roots of Chebyshev polynomials, which are known for minimizing the maximum error in polynomial interpolation.
Right.
This helps to reduce something called the Runge phenomenon,
Okay.
where you can get oscillations at the edges of the interpolation interval when you're using equally spaced nodes. In the context of DiscoTEX, using Chebyshev nodes for spatial discretization helps to improve the accuracy of the solution, especially when you're dealing with potentially discontinuous solutions.
Okay, that makes sense. Now let's talk about those discontinuities, those jumps that are mentioned throughout the paper. They seem to be a key ingredient in DiscoTEX's ability to handle those abrupt changes that happen in the solution. They even allow for user-specifiable jumps. How are those calculated, and how are they incorporated into the algorithm?
The jumps are actually calculated using a recurrence relation.
Okay.
So you start with an initial value for the jump, and then you apply this relation iteratively to calculate the subsequent jumps. What's interesting is that the number of jumps that you include is a user-specifiable parameter. This gives you control over how accurately you want to model those discontinuities. But as you might expect, increasing the number of jumps also increases the computational cost.
That's a classic trade-off.
Exactly.
Accuracy versus cost. It seems like the ability to fine-tune those jumps is one of the strengths of DiscoTEX. But before we get too deep into the implementation, let's move on to the temporal side of things.
Okay.
They use a discontinuous approach based on Hermite interpolation for time integration. What's the rationale behind that choice, and how do they extend it up to 12th order?
Hermite interpolation is a really powerful technique that uses both the function values and its derivatives to approximate a function.
Okay.
In the context of DiscoTEX, this means using not just the solution values at previous time steps, but also the time derivatives of the solution.
Right.
This allows for a more accurate approximation of the solution's behavior.
Agreed.
Especially when you're dealing with high-order methods, the paper extends this Hermite interpolation approach to achieve 12th order accuracy in time.
Wow.
Which is quite remarkable. This involves deriving and implementing some rather complicated formulas for the coefficients of the Hermite interpolating polynomial, but the payoff is a really significant improvement in accuracy for long-term simulations.
Okay, so By incorporating the derivatives, they essentially give the algorithm more information to work with, leading to a more precise approximation of the solution's evolution over time.
Yeah.
That's really elegant.
It is.
Now, with these high-order methods in both space and time, we're bound to run into that computational cost issue again.
Right.
They dedicate a good portion of the paper to exploring this trade-off. What were some of their key findings when pushing DiscoTEX to such high orders?
So the paper highlights a critical trade-off. While higher-order methods generally improve accuracy, they also come with a pretty significant increase in computational cost. They conducted several numerical experiments to evaluate the performance of DiscoTEX at different orders, focusing on the distributionally sourced wave equation as a test case.
Why the wave equation specifically?
Well, the wave equation has known exact solutions, which allows them to directly compare the numerical solutions obtained with DiscoTEX to the true solution, providing a precise measure of the algorithm's accuracy. They ran simulations with different numbers of nodes, jumps, and time step sizes, and analyzed how the error in the solution decreased as they increased the order of the method.
So there's essentially measuring how quickly the numerical solution converges to the exact solution as they crank up the accuracy.
Yeah.
What did they discover about this convergence behavior at those higher orders?
They found that, as expected, the higher order implementations of DiscoTEX did lead to faster convergence rates.
Okay.
This means that for a given desired level of accuracy, you can achieve it with fewer spatial nodes and larger time steps when using a higher order method.
That's great. So even though the individual time steps might be more computationally expensive, you need fewer of them overall to achieve a certain accuracy level.
Exactly. However, the paper also stresses that this faster convergence comes at a price. The computational cost per time step increases significantly as you go to higher orders. This means that for certain problems, like modeling those highly eccentric EMRIs, the benefits of faster convergence might be outweighed by the increased cost per time step. They found that for those types of problems, sticking with a lower order implementation of DiscoTEX might actually be more efficient overall.
So it's a balancing act. The sweet spot for the order of accuracy depends on the specific problem you're trying to solve. It's fascinating how they really delve into these practical considerations.
Yeah.
Before we move on to the nitty-gritty of their numerical experiments, I want to touch on one more thing.
Yep.
The paper mentions visualizing the results using plots and figures. I'm curious to get a sense of what these visualizations look like and what insights they provide. Can you walk us through some of the key figures and help us paint a mental picture of these results?
Absolutely. Let's start with figure 2.
Okay.
It shows the numerical weak form solution obtained with DiscoTEX H6, meaning the version of the algorithm using a 6th-order Hermite integrator for the temporal discretization. The left side of the figure depicts a 2D color map representing the field E, which in this case represents the gravitational wave, for a point particle source moving along a linear trajectory.
So this is a visualization of the wave itself as it propagates through space and time.
Yes.
What exactly are we seeing in this color map?
So the color map represents the amplitude of the wave at different points in space and time. You can think of it as a snapshot of the wave pattern at a specific moment in time. The brighter colors correspond to regions of higher wave amplitude, while the darker colors represent regions of lower amplitude. You can clearly see the characteristic wave fronts emanating from the moving source, spreading outward in a V-shaped pattern.
I can almost see it. Now, what about the right side of figure 2? It shows something called a waveform. What is that exactly?
So the waveform is a 1D plot of the wave's amplitude as a function of time, at a fixed point in space. It's essentially what a gravitational wave detector would see as the wave passes by. In figure 2, the waveform shows a smooth, oscillating signal, reflecting the periodic nature of the wave generated by the moving point particle.
The waveform in figure 2 looks remarkably smooth. Does that hold true for all the different orders of DiscoTEX?
Well, remember that this specific figure uses the exact solution as initial data for the simulation. In other words, they're starting with the perfect solution.
Yeah.
And then seeing how well DiscoTEX maintains that accuracy over time. This is a good way to test the stability and accuracy of the algorithm itself. But it doesn't tell us how well it performs when we don't know the exact solution beforehand.
That makes sense. So what happens when you don't have that luxury of knowing the exact solution beforehand?
Right.
How do they assess the performance of DiscoTEX in more realistic scenarios?
That's where the numerical convergence tests come in.
Okay.
Figure 4 is a great example of this. It focuses on determining the optimal values for those control factors we discussed earlier.
Right.
The number of nodes used for spatial discretization and the number of jumps included to model the discontinuities.
Okay, let's take a closer look at figure 4. What are we seeing in these plots?
Each line on the plot represents the error in the DiscoTEX solution compared to the exact solution for different orders of the algorithm. The x-axis represents either the number of nodes used in the spatial discretization, left plot, or the number of jumps included, right plot. As you increase either of these parameters, you'd expect the error to decrease, meaning the simulation's becoming more accurate.
And that's precisely what we see in both plots, right? The lines slope downward as you move to the right, indicating a decreasing error as you increase the number of nodes or jumps.
Precisely. What's particularly interesting here is the comparison between different orders of accuracy.
Okay.
You can see that for a fixed number of nodes or jumps, the error is significantly lower for the higher order methods, especially when the number of nodes or jumps is relatively small.
Right.
This highlights the advantage of using higher order methods when you're limited in terms of computational resources.
Yeah.
You can achieve a higher level of accuracy with fewer nodes or jumps,
Okay.
which translates to faster computation times.
That's a great point. So even though the individual calculations might be more complex for higher order methods, the overall computational cost can actually be lower if you need a very accurate solution.
Exactly. However, it's important to remember that this advantage might not hold true for all problems. For certain problems, like those highly eccentric EMRIs we discussed earlier, the increased cost per time step for higher order methods might outweigh the benefits of faster convergence.
Right.
It's all about finding the right balance between accuracy and computational cost for the specific problem at hand.
Right. It's not always about chasing the highest order of accuracy. It's about finding the most efficient way to get the level of accuracy you need for your particular problem. Now, I'm curious about figure 5.
Okay.
It shows something called the numerical error as a function of the time step size for different orders of DiscoTEX. What insights can we glean from this figure?
Figure 5 is really helpful for visualizing the convergence rates of the different orders of DiscoTEX.
Okay.
Remember how we talked about convergence rates earlier?
Yes.
And how they essentially measure how quickly the numerical solution approaches the exact solution as you refine the discretization?
Yes.
Well, figure 5 shows us exactly that.
Okay, walk us through this figure. What are we seeing here?
The x-axis represents the time step size,
Okay.
and the axis represents the error in the solution. Each line on the plot corresponds to a different order of accuracy for DiscoTEX. What you should notice is that the lines have different slopes.
Okay.
The steeper the slope, the faster the convergence rate.
I see. So the second order method, represented by the line labeled DiscoTEX H2, has the shallowest slope, indicating the slowest convergence rate. As we move to higher orders, the lines get progressively steeper, showing that we're getting closer to the true solution more rapidly as we decrease the time step size.
Precisely. This figure nicely illustrates the advantage of using higher order methods when you need high accuracy. Even though those higher order methods might be more computationally expensive per time step, their faster convergence rates can lead to shorter overall computation times, especially when you need a very accurate solution.
This is all incredibly insightful. It's like we're getting a sneak peek into the inner workings of this powerful algorithm.
Before we wrap up this part of our deep dive, is there anything else in these figures that you find particularly interesting or that you think our listeners should pay attention to?
One detail I find particularly interesting is the behavior of the error curves in figure 4.
Okay.
As you increase the number of nodes or jumps, you can see that initially the error decreases rapidly as you add more nodes or jumps, but after a certain point, the rate of decrease slows down, and eventually adding more nodes or jumps doesn't significantly improve the accuracy anymore.
Right.
This is important to keep in mind when choosing the optimal discretization parameters for a given problem.
That's a great observation. It highlights the fact that there's a point of diminishing returns when it comes to increasing the resolution of your simulation. Adding more nodes or jumps beyond a certain point doesn't necessarily translate to significantly better accuracy, but it does increase the computational cost. Exactly. It's all about finding that sweet spot where you get the best balance between accuracy and computational efficiency.
This has been an incredible deep dive so far. I feel like we've already gained a solid understanding of the core concepts behind DiscoTEX and how it achieves such impressive accuracy. but I'm eager to delve even deeper into the mathematical details of the algorithm and explore some of its potential applications. So, for now, we'll take a short break, but we'll be back soon to continue our exploration. Stay tuned.
So picking up where we left off, one thing that really stood out to me in this paper is the in-depth discussion of those intricate time jumps, specifically equations 8.26 through 8.37 in the appendix.
Okay.
They provide these explicit expressions for the time jumps, denoted as J0 through U0.
Right.
These equations are kind of the mathematical workhorses behind accurately modeling those abrupt changes that occur as the source particle moves through the simulation grid in time.
You're right. Those equations are quite a sight.
Yeah.
They're not just simple numbers. They involve trig functions and even complex numbers.
Yeah.
I have to admit, seeing complex numbers pop up in these calculations piqued my curiosity. What role do they play in capturing the dynamics of these gravitational waves?
That's a great question. Complex numbers with their imaginary unit I are incredibly useful for representing oscillations and waves. In this case, they capture the oscillatory nature of the gravitational waves generated by that moving source. Using complex exponentials allows for a compact and efficient representation of the wave's phase and amplitude, simplifying the mathematical manipulations involved in the algorithm.
I see. So it's not just about making the equations look fancy, it's about leveraging the power of complex numbers to represent the physics more effectively. But I'm still trying to wrap my head around how these time jump equations are actually integrated into the simulation. Can you walk me through that process?
Of course. Remember that DiscoTEX employs a method of lines approach, where both space and time are discretized. These time jump equations come into play during the time integration process.
Okay.
Specifically when that source particle crosses a grid point in time.
So imagine the simulation is running smoothly, marching forward in time, and then suddenly the source particle jumps over a grid point. That's when those time jumps kick in to ensure the solution remains accurate.
Precisely. At those critical moments, the algorithm calculates the appropriate time jumps. Using those equations we discussed, specifically 8.26 through 8.37, these calculated jumps are then incorporated into the solution to account for that abrupt change caused by the source particle's motion.
It's amazing how much intricate mathematical machinery is working behind the scenes to keep those simulations on track.
It is.
The paper also mentions that these time jump equations need further modification.
Right.
To include the differential operators from the wave equation. Why is that necessary?
That's an excellent point. Equations 8.38 through 8.49 in the appendix showcase this modification process. Essentially, each jump term is expanded to incorporate contributions from the spatial derivatives present in the wave equation. This ensures that the jumps accurately reflect not just the source's motion, but also the way the wave itself is evolving in space.
So it's not just about the source jumping across grid points.
Right.
It's about the wave itself changing shape and amplitude as it propagates.
Yeah.
And those spatial derivatives capture those subtle changes.
Exactly. It's a beautiful reminder that both the spatial and temporal aspects of the wave equation are deeply intertwined. And the algorithm needs to account for both to provide a faithful representation of the physics. Ignoring those spatial derivatives would lead to inaccurate jumps.
Right.
And consequently, an inaccurate solution.
It's truly impressive how the authors have managed to weave together all these intricate mathematical details into a coherent and powerful algorithm. Each piece of the puzzle seems carefully chosen to address a specific challenge in modeling these complex systems. Now, shifting gears a bit, the paper also delves into the potential applications of higher-order DiscoTEX, highlighting those trade-offs between accuracy and computational cost. They emphasize that selecting the appropriate order of accuracy hinges on the specific problem being tackled.
Absolutely. For instance, when modeling highly eccentric EMRIs, the computational expense of using very high orders might not be justifiable, given that the rapid changes in the source's motion already introduce significant numerical challenges. However, in scenarios like XMRIs with nearly circular orbits or black hole spectroscopy, where the dynamics are smoother and long-term accuracy is paramount, the faster convergence offered by higher orders could be a game changer.
It's all about choosing the right tool for the job. And DiscoTEX offers a versatile toolkit with a range of options to suit different needs. Before we wrap up this part of our deep dive, is there anything else in the paper's discussion of applications that particularly caught your attention?
One point that I found particularly insightful is the emphasis on comparing DiscoTEX with other established numerical techniques.
Yeah.
The authors advocate for future research, focused on benchmarking DiscoTEX against existing algorithms to rigorously assess its strengths and weaknesses.
I see.
This comparative analysis will be crucial for determining where DiscoTEX truly shines and identifying areas for potential improvement.
That's a crucial step in the development of any new algorithm, right? Putting it through its paces in a head-to-head comparison to see how it stacks up against the competition.
Exactly.
This kind of rigorous benchmarking will help researchers decide when DiscoTEX is the best tool for the job and when other approaches might be more suitable. It also helps to guide future research directions.
Exactly.
Highlighting areas where the algorithm could be further refined or optimized.
Understanding how DiscoTEX performs compared to other methods in various scenarios will be invaluable for researchers. Working on a wide range of problems in astrophysics and beyond, it's an exciting prospect to see how this algorithm will be used and further developed in the years to come.
I completely agree. This deep dive has been incredibly illuminating so far, and I'm eager to continue our exploration. But for now, let's take a short pause to gather our thoughts and prepare for the final leg of our journey into the world of DiscoTEX. We'll be back soon to wrap things up and delve into some final thoughts on this remarkable algorithm. Stay tuned. Welcome back to our deep dive into DiscoTEX. We've covered a lot of ground, really gotten into the mathematical nuts and bolts.
They have.
But I'm curious, what does it all mean? What are the implications of this work for our broader understanding of the universe?
Well, that's where it gets really exciting. DiscoTEX isn't just a mathematical exercise. It's a tool that could potentially revolutionize our understanding of some of the most extreme phenomena in the cosmos. Think about those extreme mass ratio inspirals and extreme mass ratio bursts we talked about earlier. Events where a small black hole spirals into a supermassive one, releasing a burst of gravitational waves. These events are incredibly difficult to model accurately, but they hold the key to unlocking secrets about gravity in the strongest regimes imaginable.
And those gravitational waves, they carry so much information.
They do.
About the objects that generated them.
But
the signals are often faint and distorted. Especially from these extreme events. So having accurate simulations is absolutely crucial for deciphering those signals and extracting meaningful information.
Exactly. That's where DiscoTEX comes in. By providing a way to model these systems with higher accuracy and efficiency, it could significantly enhance our ability to interpret the data from current and future gravitational wave detectors. This could lead to groundbreaking discoveries about the properties of black holes, the nature of gravity, and even the evolution of the universe itself.
It's like having a more powerful lens to focus those faint whispers from the cosmos, allowing us to see further and clearer than ever before. It's truly remarkable. I'm particularly intrigued by the potential applications of DiscoTEX in black hole spectroscopy. You mentioned this earlier. Can you elaborate on what that is and how DiscoTEX could make a difference in that field?
So black hole spectroscopy is a fascinating and rapidly evolving field. It involves studying the light emitted from the regions surrounding black holes to probe their properties, but these signals are often faint and distorted by the intense gravity near the black hole, making them incredibly challenging to interpret.
So it's like trying to listen to a faint melody being played on a distorted radio. You need a way to filter out the noise and reconstruct the original signal. Is that where DiscoTEX comes in?
Precisely. By providing highly accurate simulations of the dynamics of matter. In these extreme environments, DiscoTEX could help us disentangle those complex signals and extract valuable information about the black hole's mass, spin, and even its surrounding environment.
It's like having a computational magnifying glass to zoom in on those distorted signals and reveal the hidden secrets of these enigmatic objects. Beyond black hole spectroscopy, are there any other promising avenues where you see DiscoTEX making a significant impact?
One area that the paper briefly touches upon is the potential application of DiscoTEX in calculating something called the self-force. This is a fascinating concept in general relativity.
Yeah.
Describes the gravitational force exerted by an object on itself.
Wait, an object pulling on itself? That sounds a bit mind-boggling.
It is a bit counterintuitive, but in the strong gravity near massive objects like black holes, the self-force can become a significant factor.
Okay.
And accurately calculating this force is crucial for predicting the motion of objects in these extreme environments.
So DiscoTEX's ability to handle those abrupt changes in discontinuities could make it a powerful tool for tackling self-force calculations.
That's the idea. It's still early days for this particular application, but it's definitely an area worth watching. If DiscoTEX proves successful in this domain, it could open up new avenues for understanding the intricate dance of objects in the most extreme gravitational environments.
It seems like every time we peel back a layer of DiscoTEX, we uncover even more potential. It's a testament to the power of combining elegant mathematics with computational prowess to tackle some of the most fundamental questions about our universe. This has been an incredible journey, and I feel like we've only just scratched the surface of what DiscoTEX is capable of.
I agree. This algorithm has the potential to revolutionize our understanding of gravity, black holes, and perhaps even the very fabric of space-time.
Wow.
It's an exciting time to be a researcher in this field, and I can't wait to see what the future holds for DiscoTEX and the discoveries it may unlock.
It's been a privilege to share this exploration with our listeners. We hope you've enjoyed this deep dive into the world of DiscoTEX. Who knows, maybe one of you will be inspired to make the next breakthrough in numerical astrophysics. Keep exploring, keep questioning, and keep looking up at the stars. Until next time.
Welcome back for another deep dive. Today we're looking at DiscoTEX.
DiscoTEX.
Yeah, a numerical algorithm that's used for solving differential equations,
Right.
which pop up kind of everywhere in math.
Yeah, all over the place.
And, since you're all math experts already, we're going to skip right to the good stuff today.
Let's get into it.
And we're looking at a research paper that really pushes this DiscoTEX algorithm to some new limits, exploring its higher order capabilities.
Yeah, it's always really cool to see what happens to these algorithms when you kind of crank up the complexity.
Yeah, exactly. The paper is called Discontinuous Collocation, an implicit-turned-explicit IMTEX integration. Symplectic, symmetric numerical algorithms with high-ordered jumps for differential equations. 2 time integration extension to higher orders of numerical convergence.
It's a mouthful,
Yeah.
but it sets the stage pretty well.
Yeah, it does. And essentially, they're taking DiscoTEX to the next level, trying to extend it to get even higher orders of accuracy. And they picked a specific problem to test it on, which is the distributionally sourced wave equation.
Okay.
And I thought it was interesting that they picked this because it is known exact solutions.
Oh, okay.
So they can really see how well DiscoTEX is performing.
It's a smart move because you need that benchmark, don't you, when you're evaluating the accuracy of a numerical method?
Exactly. And throughout the whole paper, they keep comparing the performance of DiscoTEX at these different orders and looking at that trade-off between accuracy and computation time.
Right, because that's always the dilemma, isn't it, with numerical methods?
Yeah.
Sometimes you have to sacrifice a little accuracy to get the results you need in a reasonable time frame.
Exactly. So let's jump into the paper.
Okay.
They start off by giving a nice, concise overview of DiscoTEX, and they actually call it
Yeah,
the
really.
DiscoTEX numerical recipe in a nutshell.
I like that.
Yeah, it's cute.
It's a good way to describe it without getting too bogged down.
They explain that DiscoTEX focuses on finding numerical weak-form solutions, which is a way to handle solutions that might have these sudden jumps or discontinuities.
Right, because a lot of the traditional methods really struggle with those abrupt changes.
Exactly.
So this is a much more flexible approach.
And to achieve this, they combine spatial discretization using discontinuous collocation methods with a time integration technique called IMTEX.
IMTEX.
Yeah, which stands for implicit-turned-explicit Hermite formulas,
Okay.
corrected for discontinuities.
Yeah, they really packed it all in there.
I know, it's a lot.
It's a really powerful combination, though, isn't it?
Yeah.
Because you've got the discontinuous collocation method, which is perfect for handling jumps in space.
Yeah.
And then you've got the IMTX Hermite formulas, which is a really elegant way to do the time integration, even with discontinuities.
Exactly. And they point out these 3 key factors that we can tweak
Oh.
to influence how well DiscoTEX performs.
Oh, like tuning knobs.
Yeah, exactly. So you have the number of nodes,
Okay.
you have the number of jumps, and you have the time step size.
Okay.
So the number of nodes determines the resolution of the spatial grid.
Oh, okay.
So more nodes means a finer grid, so you get more accuracy.
Right. Yeah.
But it also means more computational cost.
Yeah, like choosing a higher resolution image, you get more detail.
Exactly.
But the file size is bigger?
Exactly. Then there's the number of jumps, which controls how DiscoTEX handles those discontinuities.
Right.
So more jumps means it's more nuanced,
Okay.
but it's also more complex.
More calculations.
Exactly. And then finally, there's the time step size, which affects the accuracy of the time integration.
Okay.
Smaller time step size means typically higher accuracy, but it takes longer to compute.
So it's always that balance, isn't it?
It's always that trade-off.
Accuracy versus speed.
Exactly. So after laying out this recipe, they dive into the heart of the matter, which is discontinuous time integration using Hermite interpolation.
Okay.
And this is where they get into the mathematical nitty-gritty.
This is where we see the elegance of the approach.
Yeah.
Because they're constructing the solution in pieces, right? And they're using polynomials to represent it between the jumps.
Right, and those jump conditions,
Yeah.
those abrupt changes are incorporated directly into these polynomials.
Precisely. They're not trying to smooth over those jumps or anything.
Right.
They're embracing them as part of the solution.
Exactly.
And you know what I really like is that they provide the actual equations that you
Yes.
need to construct these polynomials,
Yeah.
which is super helpful if you actually want to implement this method.
It's like a blueprint
Yeah.
to build these polynomial pieces.
Exactly.
And then to demonstrate that this whole approach actually achieves that higher order accuracy that we're looking for. They use a really clever example involving time-dependent Legendre polynomials.
Legendre polynomial.
It's a classic.
It's a brilliant choice
Yes.
because they have these well-known properties and they form a complete orthogonal set.
Yeah.
So they deliberately introduce a discontinuity
Okay.
into this Legendre polynomial, and then they calculate the exact jump conditions. So it's like a controlled experiment where they know exactly what the jump should be.
Yeah.
So they can compare it to what the algorithm calculates.
Exactly. And what they find is that as they increase the order of the method, the numerical solution converges towards that exact solution at the expected rate.
Oh, that's good.
Yeah. And they actually visualize this convergence in a figure and a table showing how the accuracy goes up and the computational cost also goes up as that order increases.
Right. It's that trade-off again.
It is.
But it's good to see that it's working.
Yeah. So now, having laid out this mathematical groundwork, they move on to applying DiscoTEX to a specific type of wave equation.
Okay.
A type I wave equation with the distributionally sourced term.
Okay.
And this is where things got really interesting for me.
Yeah.
Because they're tackling a problem that's relevant to some pretty hefty physics,
Oh, like what?
like gravitational waves.
Wow. So this is real-world application stuff.
Yeah, it is. And they're very transparent about their setup. They
Right.
provide the specific coefficients that define this wave equation.
Okay.
And even the coordinate system they're using, which is hyperboloidal coordinates.
Hyperboloidal coordinates. Now, those are particularly useful, aren't they? When you're studying things that radiate outwards, like gravitational waves.
Exactly, because they naturally handle that asymptotic behavior
Right.
of the solution.
Exactly.
And they even go a step further and provide the scry fixing technique
What fixing?
that they use to map the physical space-time onto these hyperboloidal coordinates.
It's great that they're including all these details.
Yeah. It's a really thorough paper.
It is.
Then they go on to the initializing jumps,
Okay.
which are designed to account for the presence of a point particle source.
Okay. So they're adding in this,
Yeah, it's like this tiny little wrinkle you need to add to get the physics right.
to capture it accurately.
And they explain how these jumps are basically corrections to the spatial and temporal discretizations.
So they're making sure that the algorithm can handle it.
You can handle the discontinuity introduced by that point particle.
Okay.
And then they talk about needing to introduce these higher order time derivative source terms
Okay.
to match the higher order time integration schemes.
It's all about consistency, isn't it?
It is.
Making sure everything is working together.
Exactly. And they provide all those mathematical expressions for those corrected differential operators and the jump corrections.
It's quite a lot of math
It is. But it's all there if you want to dive in.
if you want to get into the details.
Exactly. And then finally, they present the complete form of the DiscoTEX H6 algorithm,
Okay.
which is like the culmination of all this work, a precise mathematical blueprint for applying DiscoTEX at the sixth order.
That's impressive.
It is. And they even mention that higher-order implementations require even more jump terms, and they point us to an appendix if we're eager to explore further.
Sounds like they're inviting us along on the mathematical journey.
They are. But before we get too far ahead of ourselves, let's see how those higher-order implementations actually perform when you put them to the test.
Yeah, let's see how they do in practice.
Right, because that's the real exciting part.
Exactly.
To see if they actually live up to the expectations.
I'm curious to see the results. Now we're getting to the good stuff, the numerical experiments. They don't just lay out the math, they actually want to see how this thing performs in action.
Yeah, take it for a test drive.
Exactly, and they're very specific about their goals here. They want to demonstrate the machinery for implementing DiscoTEX at these higher orders and then compare how the different implementations stack up against each other.
Right.
So it's one thing to develop the math, but it's another thing to actually see how it behaves in practice, you know?
Yeah, for sure.
And they start by showing us the solution obtained with DiscoTEX H6 in a couple of figures. And reassuringly, the results are consistent with what they found in their previous work with the lower order H4 implementation.
It's good to see that consistency.
Yeah, it builds confidence, doesn't it?
Definitely.
That the approach is sound.
Yeah, and they're very mindful of optimizing their setup.
Right.
You know, remembering those 3 control factors that we talked about.
Yeah, the number of nodes, the number of jumps, and the time step size.
Yeah.
They come back into play here.
Like fine-tuning an engine.
Exact.
To get the best performance.
And they also remind us about the relative error calculation, you know, which is how they measure the accuracy of the numerical solution compared to that exact solution.
Right. It's their yardstick for how close they're getting.
Yeah, exactly. And to make sure the comparison between the different order implementations is fair, they use the same time step size as in their earlier work. So they're keeping things consistent.
Apples to apples.
Exactly.
So what do the results show?
Well, the results of their analysis are shown in a figure. And it's quite interesting, actually. The higher order algorithms, they don't really drastically improve over DiscoTEX H4. They kind of converge in a similar pattern, but without a significant jump in accuracy.
Huh. That's surprising.
Yeah, it is a bit, isn't it? You would think that more complexity would lead to better results, but
Not necessarily.
not in this case.
So how about the computation time?
Ah, yes. Well, that's where it gets even more interesting. They've got a table that shows the computation times. And the data clearly shows that beyond the 6th order algorithm, the accuracy kind of plateaus, while the computation time just keeps climbing.
So you're hitting that point of diminishing returns.
Exactly. You're putting in more computational effort.
Yeah.
But you're not getting much more accuracy out of it.
Now, I noticed they didn't explicitly show checks for the solution at the limits of the point particle position.
Oh, you're right. They do mention that, though.
Okay.
They explain that it's a fairly straightforward calculation.
Okay.
And the procedure mirrors what they outlined in their first paper.
So they're not belaboring the point.
Exactly. They're focusing on what's new and what's different in this work.
And they're very transparent about the fact that they included results for interpolation at the particle value.
Yes.
When they were assessing that numerical optimization.
Yeah, it's good. They're being upfront about that.
It's all about presenting a complete picture.
Exactly. Transparency is key.
So having seen the results of their numerical experiment,
That's great.
let's move on to the conclusions.
Yeah. What are the takeaways?
Yeah. What did they learn from all this?
Well, they wrap up with a nice, concise conclusion, summarizing their key findings. And they reiterate that the main takeaway is the significant increase in computation time.
Right.
And the plateauing of accuracy as you go beyond that 6th order implementation.
So bigger isn't always better.
No, it's not. And they've laid out the mathematical framework for implementing DiscoTEX at these higher orders, including those time jumps that arise from a time-dependent point particle trajectory. But they've also been very upfront, haven't they, about the computational cost that comes with that added complexity.
So they're not saying higher order implementations are useless.
Right.
But they're urging us to think carefully about the trade-offs.
Before diving in.
Exactly. Before going down that rabbit hole.
They even give us some practical guidance. You know, they suggest that for scenarios involving those time-dependent point particle trajectories, like if you're modeling those highly eccentric extreme mass ratio inspirals, it might be wiser to stick with the lower order versions of the algorithm.
Especially if you're dealing with those computationally intensive calculations.
Right. It's about choosing the right tool for the job.
Right. Sometimes a simpler tool can get the job done.
Yeah.
Just as well, if not better than a more complex one.
But they also acknowledge that, as you would expect, the higher order implementations, they do tend to achieve higher accuracies more quickly for longer time steps.
Okay.
So they suggest that this faster convergence could be valuable in other astrophysical modeling scenarios,
Like what?
like those extreme mass ratio inspirals with slowly shrinking circular orbits.
Okay.
So it depends on the specifics of the problem you're trying to solve.
So the characteristics of the problem dictate whether those higher order implementations are worth it or not.
Exactly. And they even hint at another potential application
Really?
for this discontinuous or even the smooth IMTEX Hermite time stepper.
Which is,
Black hole spectroscopy.
wow. So they're branching out.
Yeah, it's really interesting.
That's exciting.
It is. It's like they've opened up a whole new avenue of exploration.
So what are the key takeaways then from this whole discussion of their numerical experiments?
Well, I think the main takeaway is that they've shown that for time-dependent point particle trajectories, those lower order implementations of DiscoTEX, particularly H4,
Yeah.
offer a good balance
Okay.
between accuracy and computational cost.
So it's not always about going higher and higher.
No, sometimes simplicity wins.
Yeah, it's a valuable lesson.
It is. Yeah, it really makes you think about the decisions researchers have to make, don't they, when they're designing these algorithms? You know, it's not always about pushing for the highest order possible. It's about finding that sweet spot
Yeah.
between accuracy and efficiency and what the problem actually demands.
Yeah, it's a really nuanced perspective. And I think a lot of people who aren't, deep in the world of numerical analysis,
Right.
they might not appreciate that.
Yeah, they might just assume that more complex is always better, but
Yeah.
that's not always true, is it?
No, it's not. It's like choosing the right tool from a toolbox. You wouldn't use a sledgehammer
Exactly.
to drive in a tiny little nail.
You need a more delicate tool sometimes.
Yeah, exactly. So for our listener, who's really into math, what would you say is the most surprising finding from this paper?
I think for me, it was the unexpected performance of those higher order implementations.
Yeah.
Going in, you'd assume that if you crank up the order, you're going to get much better accuracy.
Right.
But the results show that's not always the case. Yeah.
And in fact, for some problems, those lower order implementations might be the better choice.
So you really have to analyze it carefully.
Yeah, you can't just rely on assumptions.
And test it out.
Exactly.
Speaking of testing, I was really intrigued by their mention of black hole spectroscopy as a potential application.
Oh, yeah.
For these time-stepping methods, can you tell us a little bit more about that?
Yeah, so black hole spectroscopy is this fascinating field where you're studying the light that's emitted from the region around a black hole
Okay.
to learn about its properties like its mass and its spin.
Okay.
But the challenge is that this light is being bent and redshifted in all these complex ways.
Yeah, because of the gravity.
Exactly, because of that intense gravitational field.
Yeah.
So to model this accurately, you need to solve these equations that describe how light propagates
Yeah.
in this curved spacetime.
And those equations are really complicated.
Oh, they're very complex, and you need some pretty sophisticated numerical methods to solve them.
So that's where DiscoTEX comes in. Exactly. Or even just the IMTEX Hermite time-stepping technique.
Okay.
Because its ability to handle those discontinuities and those jumps
Yeah.
could be really useful for modeling scenarios where the light is being emitted from a source that's moving really rapidly or erratically,
So it's capturing those sudden changes in the light's path.
precisely as it interacts with that gravitational field.
And black holes are such extreme environments
They are.
that even small inaccuracies can lead to big errors.
Exactly. So having a method like DiscoTEX that can handle those tricky situations
Yep.
could be a game changer for black hole spectroscopists.
Yeah, it's like the perfect match.
It is.
This powerful algorithm for this really challenging problem.
And that's just one example,
Yeah.
The authors suggest that there might be other applications in astrophysics and beyond.
It's amazing how much potential there is.
It is. It's really exciting.
It's a testament to that curiosity-driven research.
Yeah.
You never know what you're going to find when you start digging deeper. So to wrap things up, I think we've done a really thorough deep dive into this paper today.
I think so.
We've covered the math, the surprising results, and even peek into the future,
Yeah.
and the potential applications of this fascinating algorithm.
It's been a pleasure talking about all this with you.
Yeah, it's always fun to explore these really cutting-edge topics.
It is.
And for our listeners out there, we hope this deep dive has given you a new appreciation for the beauty and the complexity
Yeah.
of numerical analysis and how important it is for understanding the universe.
That's crucial.
We encourage you to check out the full research paper for yourself
Yeah.
And as always, keep those minds curious.
Keep exploring.
And we'll be back with another deep dive soon. Welcome back, learners. Ready for another deep dive?
Always.
Today we're going deep into a world where math gets real in astrophysics.
Sounds intense.
It definitely is, especially with this paper. DiscoTEX 1.0. Discontinuous collocation and implicit-turned-explicit IMTEX integration, symplectic symmetric numerical algorithms with high-order jumps for differential equations. 2. Time integration extension to higher orders of numerical convergence.
Okay, that's a mouthful, but I think I get the gist. Numerical methods for tough problems, right?
Right. It's all about how mathematicians are pushing the limits to model the most extreme events in the universe, stuff we could only dream of simulating accurately before.
And what grabbed my attention right away is how this paper tackles a core challenge in numerical analysis. Finding accurate solutions to PDEs, those partial differential equations that have sudden jumps or discontinuities.
PDEs. Those can be tricky even without jumps. So remind me why those discontinuities are such a pain to deal with.
Well, imagine you're modeling the ripples in a pond after tossing in a rock.
Okay, peaceful scene. Got it.
Now, swap that rock with a tiny black hole with a crazy strong gravitational field.
Uh-oh, things just got serious.
That black hole, being essentially a point, creates a discontinuity, a sudden, sharp change in the otherwise smooth fabric of space-time. That makes the math a whole lot harder to work with.
So it's not just about solving the equations, it's about solving them in a way that captures those sudden shifts caused by the black hole.
Exactly.
And this is where DiscoTEX steps in, right?
You got it. DiscoTEX, short for discontinuous collocation, and IMTEX, is built to find what we call weak form solutions to those kinds of PDEs.
Weak form solutions. That rings a bell. Can you refresh my memory on that?
Sure. It's a way to find solutions that still satisfy the PDE in a broader sense, even when there are those jumps that make the usual methods go haywire. It's particularly good for PDEs with distributional sources, a fancy way of saying those point-like objects causing all the trouble.
Ah, right. Like our tiny black hole friend. So we have these complex PDEs representing the gravitational field around the black hole, and we need this special solution, a weak form solution, to handle the abrupt changes it causes. But how does DiscoTEX actually go about finding it?
DiscoTEX uses a clever approach called the method of lines framework. It breaks the problem down into 2 steps. First, discretizing space by dividing it into a grid of points, and then tackling time separately.
A divide and conquer strategy for mind-bending math. I like it. But can you break those steps down a little more? How does it handle space first?
For the space part, DiscoTEX uses discontinuous collocation methods based on Lagrange interpolation.
Lagrange interpolation. Flashback to numerical analysis class. It's like building a bridge between data points, right?
Exactly. The PDE gives you relations between the solution and its derivatives at different points in space, and DiscoTEX uses Lagrange interpolation to fill in the gaps between those points, creating a smooth approximation of the solution across the whole grid.
Okay, that makes sense. But we're dealing with discontinuities. How does Lagrange interpolation handle those sudden jumps?
That's where the discontinuous part of discontinuous collocation comes in. Instead of forcing one single polynomial to fit across the entire grid, which wouldn't work with those jumps, DiscoTEX allows for different polynomials in different regions of the grid.
Ah, so it's like using multiple smaller bridges to span those gaps, allowing for the abrupt changes in the terrain. Smart. But what about time? How does DiscoTEX handle that?
It uses something called IMTEX, Hermite formulas for the time integration. IMTEX stands for implicit-turned-explicit, a technique for efficiently solving the equations. And Hermite formulas are great for handling those discontinuities.
Hermite formulas. Vaguely familiar. Remind me how those work and why they're good for jumps.
They're based on Hermite interpolation, similar to Lagrange, but it also factors in the derivatives of the function at the known data points.
So we're adding information about the rate of change, right?
Exactly. That extra information lets Hermite formulas capture those sudden shifts in the solution much better.
I see. So it's not just about connecting the dots. It's about connecting them while respecting the slope and curvature, especially where things are changing rapidly. It's getting quite complex, but I'm starting to grasp the sophistication here.
It gets even more complex. The researchers took it further by developing high-order IMTX Hermite formulas.
Higher order. Does that mean they're using even more advanced math to make the approximations even more accurate?
Exactly. They're essentially using higher degree polynomials in their Hermite formulas, allowing them to capture finer details and reduce errors associated with those discontinuities.
So it's like using a finer brush to paint those bridges between the data points, making the approximation even smoother and more accurate. But I imagine that comes at a cost, right? More accuracy usually means more computation.
You're right. Higher order methods generally require more computational resources, but that's a trade-off researchers often make, especially with complex phenomena like black hole mergers.
Right, always that balance to strike. But before we get too deep into computation, one detail is bugging me. They mentioned using Chebyshev's pseudospectral collocation nodes. What are those, and why are they important for DiscoTEX?
They're the specific points in space where DiscoTEX evaluates the solution and its derivatives. Chebyshev nodes are well known for their accuracy and stability in numerical methods, particularly for interpolation and approximation.
So they're not just picking random points on the grid, they're strategically choosing them to get the best results. It's like picking the best vantage points to observe a complex phenomenon. You wouldn't just stand anywhere, you'd pick spots that give you the clearest view.
Exactly. By carefully choosing these nodes, the researchers ensure DiscoTEX is as accurate and efficient as possible. There are other factors that also influence the algorithm's performance. The control factors.
Control factors. Are those like settings you tweak to fine-tune the algorithm?
Spot on. There are three main ones. First, the number of nodes, which determines how fine that spatial grid is.
Okay, so more nodes mean a more detailed picture, but probably more computation time too.
Exactly. Second, the number of jumps, which dictates how many discontinuities DiscoTEX will handle directly.
Sounds like things can get mathematically intense as you add more jumps.
Oh, they do. And lastly, the time step size. Think of it as the intervals at which DiscoTEX captures snapshots of the solution in time. Smaller time steps generally mean higher accuracy, but again, more computation.
So it's a balancing act between precision and efficiency. We want the best results, but we also don't want our computers to melt down.
Precisely. Finding the right balance between those control factors is key to using DiscoTEX effectively.
This is starting to click. We have an algorithm that breaks the problem into space and time, uses clever interpolation techniques, and has adjustable settings to fine-tune performance. But one thing still bugs me. The paper mentions higher-order jumps. What are those, and why are they important?
Great question. It takes us deeper into DiscoTEX's math. Remember those discontinuities from the black hole? Those are the jumps we've been discussing. But to model them accurately, we need to consider their higher-order derivatives too.
Higher-order derivatives, like the rate of change of the jump itself and the rate of change of that rate of change. My head is spinning a bit, but I'm following you.
Exactly. It's like considering not just the position of the black hole, but its velocity, acceleration, jerk, all those higher-order variations in motion. These variations affect how the jump propagates through the PDE's solution.
Wow, that's complex. How do they even start calculating that?
They use something called a recurrence relation. It's a formula for calculating a sequence of values based on previous values in that sequence.
The domino effect, where each jump influences the next one. And they have a formula to track all those cascading effects.
That's a great visualization. The higher order jumps, those derivatives of the jump, become increasingly important as we increase the algorithm's accuracy.
So they're building a super precise model of how those jumps ripple through the solution of the PDE, including all their variations. But how do they know their calculations are right? How do you test something this complex?
They used a time-dependent Legendre polynomial, a function with known analytical jumps. This means they know exactly what the jumps and their higher-order derivatives should be.
Like a controlled experiment where they can compare their results to the exact solution.
Exactly. And the results, shown in Figure 1 and Table 1 of the paper, look great. The errors are tiny and decrease as they use higher-order jumps.
Amazing. They're creating a mathematical microscope to zoom in on those discontinuities with incredible precision. But this is all very abstract. How does this apply to real problems like modeling black hole mergers?
That's where things get really interesting. The paper focuses on solving a distributionally sourced wave equation of type I. This equation, with its source term representing the motion of a black hole, is the perfect testing ground for DiscoTEX.
A wave equation, huh? Now we're talking. Can't wait to hear how this plays out.
Let's dive into that equation and how DiscoTEX tackles it in the next part of our deep dive. Welcome back to our deep dive into DiscoTEX. Before we got sidetracked, we were talking about how DiscoTEX uses some pretty cool math to handle discontinuities in PDEs.
Those jumps.
Yeah, those jumps. Now let's see this algorithm in action. The researchers tackled a specific problem, solving a distributionally sourced wave equation of type I.
Hold on, a wave equation.
Yeah.
How do those apply to black holes?
Wave equations describe how disturbances or waves travel through a medium. They're everywhere in physics. Sound waves, light waves.
I see where you're going with this.
In this case, we're talking about gravitational waves, those ripples in space-time itself.
Right, gravitational waves. They're created by accelerating masses, like when a black hole spirals into another one. So are they trying to model the gravitational waves from a black hole merger?
Exactly, but not just any merger. They're looking at mergers with a huge mass difference, like a small black hole falling into a supermassive one.
Sounds intense.
It is. These are called extremely asymmetric binaries, and they're a nightmare to model.
So this algorithm is helping us study systems we couldn't accurately model before. That's huge for understanding gravity in these extreme environments. But what makes these asymmetric binaries so tough to model?
It's all about the speed and acceleration of that smaller black hole as it zips around the much larger one. Think of a hummingbird darting around a giant redwood tree. You need a super high-speed camera to capture all the action.
Right. The smaller black hole is moving so fast it creates those rapid jumps we talked about, requiring tiny time steps for accuracy, which drives up the computational cost.
Exactly. Traditional methods struggle to keep up with those rapid changes, but DiscoTEX, with its clever discontinuity handling, can handle these extreme cases better. It's like DiscoTEX has image stabilization for our cosmic hummingbird movie.
Nice analogy. So we've got our wave equation for the gravitational waves and our source term representing the tiny black hole's motion. But the paper also mentions scry fixing. What is that? Sounds like science fiction.
Not as exotic as it sounds, but pretty clever. Scry fixing is about picking the right coordinate system for the problem. When dealing with black holes and gravitational waves, the usual Cartesian coordinates just don't cut it.
I can imagine. Space-time gets pretty warped around a black hole. So what do they use instead?
They use hyperboloidal coordinates, which have some handy properties. For one, they naturally handle the boundary conditions at the black hole horizon.
Makes sense. The horizon is the point of no return, a natural boundary. But what about the other boundary? Gravitational waves travel outwards forever, right? Where does the simulation end?
That's where future null infinity comes in. It's where light rays end up in the distant future. Think of it like the horizon you see when looking at the ocean, where the sky and water meet, even though we know the Earth curves. Future null infinity is similar, but for light in the universe.
Okay, I'm starting to see why these hyperboloidal coordinates are so useful. They naturally incorporate both the black hole horizon and future null infinity as boundaries. But what about scry fixing? Where does that fit in?
Scry fixing simplifies things by fixing the location of future null infinity in our coordinate system. It's like setting a boundary and saying, this is where our universe ends, for this calculation at least.
So it makes the problem manageable while still capturing the essential physics. Cool.
Yeah.
But we haven't even talked about how DiscoTEX actually solves this wave equation. How does it all come together?
Remember the method of lines framework. DiscoTEX first discretizes space using those discontinuous collocation methods based on Lagrange interpolation. This gives us spatial snapshots of the solution at each grid point, respecting those black hole-induced jumps.
Right, those spatial snapshots. And then it connects them in time using the IMTEX Hermite formulas.
Yeah.
But those formulas need to be adapted for the jumps, right? How does DiscoTEX ensure the time evolution is also accurate?
That's where the higher-order corrections come in. Remember those higher-order derivatives of the jump? We have to include them in the wave equation's source term, the part representing the black hole's motion.
So they're adding more detail for super precision, like going from a sketch to a high-definition photograph.
Exactly. Equations 72 and 73 in the paper show how those corrections are added, and it gets pretty intense mathematically. But the key is that by including these higher-order terms, they dramatically improve the solution's accuracy.
Okay, I'll definitely need to revisit those equations later. But for now, how well does DiscoTEX actually perform? Does it live up to the hype?
The paper shows some visualizations of the solution in figures 2 and 3, and they highlight that the results match those from lower-order implementations. That's a good sign, suggesting DiscoTEX is at least as good as existing methods.
But they didn't stop there.
Right.
They also ran numerical convergence studies to see how DiscoTEX performs at different orders of accuracy. Remind me, what are convergence studies and why are they important?
Convergence studies tell us how quickly the numerical solution approaches the exact solution as we increase the algorithm's accuracy. Essentially, how much better our solution gets as we crank up the precision.
Got it. And what did those studies tell us about DiscoTEX? Is higher order accuracy always the best way to go?
That's where things get interesting. Figures 4 and 5 show their convergence studies, and they highlight a key trade-off in numerical analysis: accuracy versus efficiency. Higher order schemes converge faster, meaning they approach the exact solution quicker, but there's a catch.
The computational cost skyrockets.
Yeah.
That balance between precision and efficiency again.
Exactly. Table 2 shows this trade-off. A 12th order scheme might be super accurate, but it takes way longer than, say, a 4th order scheme, like choosing between a high-definition movie that takes hours to render and a standard definition movie that's ready in minutes.
I feel that. Sometimes you need to get the project done, even if it means sacrificing a bit of resolution. But for black hole mergers, wouldn't we always want the highest accuracy?
That's a good point, and it leads to one of the key insights of this research. For some applications, like those long simulations needed for extreme mass ratio inspirals, a lower order scheme might be more practical. It might not be perfectly precise, but it's good enough and much faster.
So it's about choosing the right tool for the job. That's a valuable lesson, not just for modeling, but for life, really. But before we get philosophical, there's one more thing. The paper suggests DiscoTEX could be used beyond black hole mergers. What are some of those possibilities? What else can we explore with this mathematical powerhouse?
Welcome back. Before we got off track, we were discussing how DiscoTEX is really changing the game for modeling extreme events in astrophysics, especially those involving black holes. But you were right, its potential goes way beyond just black hole mergers.
That's what I'm so curious about. We've talked about the math, the techniques, the trade-offs, but what's the big picture? What can DiscoTEX help us understand about the universe that we couldn't before?
Well, one area where DiscoTEX could be a real game changer is black hole spectroscopy.
Black hole spectroscopy. Okay, you've got my attention. What is that?
Imagine being able to hear a black hole as it vibrates after being disturbed, like a bell being struck.
Wow, okay. I'm trying to picture that.
These vibrations are called quasi-normal modes, and they hold information about the black hole's properties: its mass, its spin, all sorts of things.
So it's like using sound waves to probe the structure of something we can't see, like bats using echolocation.
Exactly. And just like different bells have different tones, different black holes have unique quasi-normal modes based on their characteristics.
Fascinating. So we can essentially listen to a black hole and learn about it. But where does DiscoTEX come in?
Simulating these quasi-normal modes accurately takes a lot of computing power, especially for black holes in complex environments or those undergoing rapid changes. That's where DiscoTEX shines, with its ability to handle those discontinuities and maintain high accuracy.
Ah, I see. DiscoTEX helps us create more realistic simulations of those vibrations so we can extract more precise information about the black hole's properties.
Exactly. And it goes beyond just individual black holes. By studying these vibrations across many black holes, we can learn how they form, evolve, and interact with their surroundings. It's like we have a cosmic orchestra, with each black hole playing its own tune.
That's a beautiful way to put it. We're using DiscoTEX to conduct a symphony of black holes, unlocking the secrets hidden in their gravitational melodies. But there were hints about other applications too, right? What else can we explore with DiscoTEX?
The possibilities are endless, really. Remember, DiscoTEX is a tool for solving PDEs with discontinuities, and these types of equations pop up everywhere: physics, engineering, even finance.
Anytime there's a system with abrupt changes or sudden events, DiscoTEX could be the key to modeling and understanding it, right?
Exactly. For example, in fluid dynamics, you could use DiscoTEX to model things like shock waves or how fluids behave in complex environments. In material science, you could simulate how cracks spread or the dynamics of materials like sand or gravel.
It's a really versatile algorithm with a huge range of applications, not just in astrophysics.
Absolutely. And as researchers continue to refine and adapt DiscoTEX, we can expect even more creative uses to emerge. It's a really exciting time to be working in numerical analysis.
It certainly is. One thing that struck me about this research is the importance of finding that sweet spot between accuracy and efficiency. It's not always about using the most complex tools, but the ones that are best suited for the specific problem.
You're right, and this research really makes us think about where to draw that line. When we're trying to model the universe, or any complex system for that matter, finding the right balance between precision and practicality is key. And that, dear listener, is something worth thinking about.
It definitely is. Thanks for joining us on this deep dive into the world of DiscoTEX. We hope you learned something new and are inspired to explore the amazing complexity of our universe. Until next time, keep learning.